Okay, so welcome back to the Advanced Linear Algebra. So what we will do is that we will carry on our discussions on Advanced Linear Algebra from the point where we left our contents physically in the class, and I hope that you are safe and sound at your home. And now it's time to return back to the work. And so the way that we are going to move forward is going to be that I'm gonna every week upload a lecture of 3 hours or maybe 2 lectures of 1.5 hours, and corresponding to each lecture I'm gonna put an exercise sheet, and your task would be to do that exercise sheet within a given timeline. And another important thing that you have to do is to read out the stuff that we are doing from the book that I said that we're going to follow. So as you remember that we are going to follow a beautiful book called A Second Course in Linear Algebra. So we will carry on doing it. So what we did last time in our class, we went in detail into the basic theory of inner product spaces and how and why inner product spaces are useful. Okay, and we kind of went into the inner product spaces, and then norms, and then the basic properties of norms and inner product spaces, and then we talked about what do you call orthogonal projections. Okay, orthogonal projections, orthogonal vectors, and several results about orthogonal projections and orthogonal vectors. So we went into the very much details of inner product spaces, norms, and orthogonal projection. And if you remember why inner product spaces are interesting, because if you want to extend, for example, so one of the reasons could be that if you want to extend your theory of geometry, the basic theory of geometry, for example, the geometry that you have in two-dimensional plane, and you want to take it into kind of the more abstract spaces. For example, you want to do the geometry on, say, curved spaces. You want to do the plane geometry, for example, on a sphere or on a torus or on some other kind of abstract space. Then inner product spaces are basically the spaces in which you can do or develop the new versions of the geometry. So we went into the details. I'm not getting into that again. So what is the agenda for today? So the agenda for today is to go through the following topics. We're gonna get into the first we will define and talk about some of the basic properties of orthonormal systems. Okay, so what do we mean by orthonormal systems? What are the basic properties of it? What is the relationship of orthonormal systems with the finite dimensional basis of the vector spaces, and basis of the finite dimensional vector spaces. So this would be the first thing that we are going to do, and then using these orthonormal systems, we will talk about what do you call orthonormal bases, as I said. So this would be the next thing that we would like to get into it, and in this we will quickly review the so-called Gram-Schmidt process. The next thing would be that we're gonna do is the Gram-Schmidt process. I'll not get into the details of the Gram-Schmidt process because I know that you have already done the Gram-Schmidt algorithm in your first linear algebra course, but I would like to show that using the Gram-Schmidt process and theory of orthonormal system, what we can show is that every finite dimensional vector space or inner product, every finite dimensional inner product space has a orthonormal basis actually. Okay, so we're going to argue for that. The next important thing, rather the serious thing that we're going to do today is we're going to cover the so-called the Riesz Representation Theorem. Okay, so this would be the next thing that we will do, and some of the consequences of Riesz Representation Theorem. So this would be something very interesting topic. Okay, and the next that we will finally do is going to talk about quickly the adjoint of linear transformations and matrices. So this would be the next thing that we're going to do, that adjoints of linear transformations and matrices, and then we will end our discussion on finally by proving Parseval identity and the Bessel's inequality. Okay, so the final topic that we're going to cover today is going to be the Parseval's identity and the Bessel's inequality. Okay. This is what we're gonna do, and maybe if there will be a time in our next discussion, I'll talk about that how all this stuff can do an amazing thing called the Fourier series. Okay, we will develop the abstract versions of the Fourier series actually, and we'll talk a little bit about it. So a big agenda. I will quickly go through this. I'll not spend too much time on it because I know that there are the things that you already know about these first three topics. The key thing would be to focus on the next three results, which are our three topics, which are the Riesz Representation Theorem and adjoints of linear transformation and Bessel's and Parseval's inequality. Okay, so let's begin with what do you mean by an orthonormal system. So I hope you all remember that what do you mean by an orthonormal a vector are two vectors. When two vectors are orthonormal, maybe we'll just extend that definition to an arbitrary number of orthonormal vectors actually. So what do you mean by an orthonormal system? So here's our first definition. So the orthonormal systems why orthonormal systems are interesting? Orthonormal systems are interesting because, for example, if you are doing geometry, you're going to take course on so-called differential geometry system. Differential geometry, you will see that the engineers, the physicists, really like the orthonormal systems actually. Why? Because the orthonormal systems makes their calculation very easy. So in other words, if you have a vector space and you want to study, for example, some physical quantity in that vector space, and you want to calculate, or prove some properties of that physical quantity that you are interested in the vector space, the calculations are going to be way easier if you choose the orthonormal basis for that vector space. But if you try to, for example, do the same calculations with any basis of that vector space, then it turns out that the calculations are pretty much what do you call messy. So since every inner product space, okay, has what do you call orthonormal basis, so whenever you want to do the calculations in inner product spaces, you prefer the orthonormal vectors, orthonormal system or orthonormal basis as basis actually for the inner product space, because it kind of radically reduce your calculations. Actually, we're going to see some of the applications of it as well. So what do we mean by an orthonormal system? So suppose you have a sequence of vectors. Okay. Suppose u1, u2, u3 is a sequence of vectors. This sequence can be finite or infinite, so there is no restriction. In other words, your inner product space could be infinite dimensional or finite dimensional. So suppose that you have a finite or infinite sequence of vectors, in inner product space. Okay. Inner product space. Then you call that this sequence of vectors in inner product space is orthonormal. Or forms an orthonormal system. So this is an orthonormal sequence, or it's an orthonormal system. Orthonormal system if the following condition holds actually. So in other words, you take, if the following is true, you take the inner product of, say, ith term of this sequence with, say, jth terms of this sequence. So you take the ith vector and take the jth vector, and it turns out that their inner product is what you call the Kronecker delta. That is that this inner product should be 1 if I and j are equal. In other words, that if you take inner product of ui with ui, you should get 1, and it would be 0 if I does not equal to j actually. So in other words, you're going to call this sequence of vectors as an orthonormal sequence or an orthonormal system if each one of these vectors has a unit magnitude. Because think about it, if ui and ui is equal to 1, because when I is j, then this should become ui and ui, and what does this mean is that then ui and ui is 1, but the ui inner product is basically ui norm square actually. We know the relationship between inner product and norm. So in other words, each one of this vector is has a unit norm, okay, and each one of these vectors is orthogonal to other vector. So in other words, u1 is orthogonal to u2. In other words, the inner product of u1 with u2 is 0, and inner product of u1 with u3 is 0, and u2 and u3 is 0, and so on and so forth. So what do we mean by an orthonormal system? So a sequence of vectors, a collection of vectors in an inner product space is going to form an orthonormal system if each one of these vectors has unit magnitude and every vector is orthogonal to every other vector. So they are mutually orthogonal to each other actually. Okay, so this is what really the definition of it. What are some of the examples of orthonormal system? So here are some of the examples of orthonormal systems. Here are some of the examples of orthonormal system. For example, if you take V as an say R2 or C2. Okay, so if it's two-dimensional plane, then we know that there is an inner product on R2. So the inner product on R2 is really, what do you call, xy, that is equal to x1 y1 plus x2 y2. In other words, it's simply dot product, where x is a vector x1 x2. Maybe I should write it here. That x is a vector x1 x2 and y is a vector y1 y2. Okay. So with this, then we know that R2 is in a product space. So in this, if you take, for example, two vectors, say u1, so the u1 is say 1 over square root 2 and 1 over square root 2, and you take u2 as minus 1 over square root of 2 and minus 1 over square root or 1 over square root of 2, then these two vectors, then this system u1 u2, the collection of these two vectors, is an orthonormal system. Is an orthonormal systems, or you can say that these two vectors are orthonormal. Why they are orthonormal? If you take their inner product, in other words, if you compute say u1 u2 by say this definition, you're going to get minus 1/2 plus 1/2, so equal to 0. And if you compute, for example, inner product of u1 with u1, you're going to get what? So you're going to get minus 1/2 square plus minus 1 over 2 square root of 2 square plus 1 over square root of 2 square, so it's going to be 1. And similarly, if you compute u2 u2, you're going to get 1 as well. So this is one example of an orthonormal system. Another example could be that if you take, for example, following sequence, okay, you take V to be say R infinity, you take V to be R infinity or C infinity, so it's a collection of infinite sequence of the tuples. Then following is an orthonormal system, so it's going to be U1, that is say 1, 0, 0, 0, U2, 0, 1, 0, 0, and U3, 0, 0, 1, 0, 0, and so on and so forth. Then this U1, this collection U2, U3 is an orthonormal system. So this is orthonormal system. Okay? Orthonormal system. So this would be an orthonormal system. Say, for example, another example could be maybe an example of infinite dimensional, also infinite dimensional in a product space. So we know about, you know, these inner product spaces, that these are inner product spaces. What are their inner products? So we covered all this stuff in our previous chapter, chapter number 4 of the book actually. Okay, so I'm not going to get into the details of everything. So I'm going to assume that you have read that chapter, you have solved the exercises of that chapter, so you know how to deal with the basic inner product spaces actually. So imagine you take V to be the space of the continuous functions defined over the interval 0 to 1, then we know that on this we have, this is the inner product space. Inner product on V can be defined as the L2 inner product. In other words, that you multiply f of t, g of t, and then integrate the product f of t, g of t with respect to say dt over 0 to 1. Then we can prove that this is V is in a product space. So in this, if you take, for example, these three vectors, these three functions, f of x, f1 of x equal to 1, and f2 of x equal to, say, 2x minus 1, and you take, say, f3 of x to be, I guess f3, take f3 of x to be 6x squared minus r. So there must be a conjugate here, because f are the functions that takes values, that takes inputs from 0 to 1, but their outputs can be r, can be set of complex numbers actually. So in other words, f is a map from, so an arbitrary element here is a map from 0 to 1 into what you call field actually, and the field could be either R or could be C. Okay, so these are, so the f of t and g of t is complex numbers. So if it is, if f is R, then this is really what you call the inner product is. But you know, if your f is a complex number, then this would be the inner product, f of t multiplied by the conjugate of g of t and the inner product. Anyway, so consider these three vectors, 6x squared minus 6x plus 1, and you can easily verify that basically that these three vectors, f1, f2, f3, form an orthonormal system actually. So in fact, what you can do using this definition, you can make calculation. You can say that f1, the inner product of f1, f2 is 0, and you know, you can prove that fi, fj is 0, where I and j are 1, 2, 3, while the inner product of, say, f1 with f1 is 1. Okay, while f1 or fi with fi is 1 actually. So you can do these calculations and check that this forms an orthonormal system. So what do you mean by simply an orthonormal system? So if you have a sequence of vectors whose magnitude is 1 and they are mutually orthogonal to each other, you're going to call that system as the sequence of orthonormal system. So what is the beautiful thing about orthonormal system? So here is one of the consequences of this, that what you can do is that if you have a finite, if you have an orthonormal system that comprises of finite number of vectors, then you can generalize the Pythagorean theorem in inner product spaces actually. So we proved the Pythagorean theorem actually. I mean, if you remember in inner product spaces, that if U is a vector orthogonal to V, then the inner product of then we proved that norm of U plus V square is equal to norm of U square plus norm of V square actually. So we proved, what do you call this, Pythagorean theorem. So what we can do is that we can generalize this result and we can prove, for example, following. So here's an immediate consequence of what we have here. So here's a theorem. Okay, so I'm going to quickly prove this theorem. So it says that, so imagine I have a finite orthonormal system. Okay, so you're not going to take an infinite sequence of orthonormal vectors, because in that case, you know, the convergence of series would be a trouble actually. So maybe we have a convergence of a series that I'm going to write, or maybe we don't have. Anyway, so imagine you have this orthonormal system. So if U1, U2, Un forms an orthonormal system, then if you take a linear combination of I equal to 1 to n, say, of a general linear combination of these vectors, any linear combination of these vectors, and calculate their what you call magnitude, then this would be equal to sum I equal to 1 to n magnitude of ai square, actually, for all a1, a2, an that are from the field. And as I said, the field could be set of real numbers or set of complex numbers, actually. So if you take an arbitrary, so you have an orthonormal system, and you take an arbitrary linear combination of it and you calculate the magnitude of it, the magnitude of it is going to be simply the sum of the squares of the coefficients here, actually. Okay, sum of the squares of the coefficient here. So this is what is going to be one of the basic consequences. Secondly, you might ask a question that why you haven't taken what you call, why this result is not true for an infinite orthonormal system. The answer is that imagine if you have an infinite orthonormal system and you try to calculate this, say I equal to 1 to infinity, then this would be equal to I equal to 1 to infinity magnitude of ai square. The trouble would be we don't know actually that whether this series converges or not. Okay, this series converges or not. So if this series does not converge, then this would be infinity and this inequality would not make sense, actually. Okay, so under certain assumption you can also extend this identity, this theorem, this generalization of Pythagorean theorem to infinite case as well, but you're going to have assumptions on AIs, actually. Okay, but for now we are proving it for the case of the finite case, actually. So what we do, how should we start? So let's start with this side. So I equal to 1 to n ai ui square. I'm going to assume that you all remember, I would suggest that before watching this lecture, please go through the chapter number 4, because I'm going to assume everything from the chapter number 4 that you have in your mind, you have the basic results in your head. I'm not gonna get into the proofs and of those results, actually. So I'm gonna simply use them. Anyway, so the magnitude of a square would be what? So we know that if I have the relationship between, in other words, the inner product induces a norm also on an inner product space. So when you have an inner product space, your inner product space is also a normed space, and the relationship is this, actually. Okay, that if you have a magnitude of some vector square, this is equal to the inner product u. Okay, so this is going to be sum I equal to 1 to n ai ui and sum I equal to 1 to n ai ui in the product. So this is what that you're going to get, actually. And then if you remember, we had two properties that if you have, say, u plus v w, then you can write this as u plus uw and vw. Okay, so inner product is linear in the first coordinate, actually. Okay, or it preserves the addition in the first coordinate, and same is the true for the second coordinate. Okay, so if you have uv plus w, then this is same as uv plus uw. We proved all these properties, in our 4th chapter. And then you also have that if you have and a scalar multiplied with u in the first component, and you have a v here, then you can pull this scalar out without any trouble. Okay, so you